All right, here it goes. Ready? And crash and burn. Okay, so here that's the short, very short trip that our remote control car made. Maybe it ran out of juice. And here it is, 3.5 feet to the right of the vertical diameter. Question. Represent in two ways the fraction of the radius that the car is to the right of the vertical diameter. So can you first let's estimate. No calculator. No calculator. This is understanding. First, estimate the fraction of the radius that the car is to the right vertical diameter. Then express that number exactly in two ways. No calculator. .5 feet to the right. I'm trying to get myself together here. Okay, so that it's 3.5 feet to the right of the vertical diameter. So I want you to estimate the fraction of the radius that the car is to the right, and then express it two different ways. Write an expression that would give that number exactly. Two different expressions. Everyone should this is test. This is fair game for the test. This is nothing new. Can you do it? If you can't do this, you're in trouble on the exam. This is basic. Basic, basic, basic. No calculators. You should know what we're talking about here. So how about the estimate? What do we think? How about, who's the lucky winner today? How about Zach? What do you think? What's your estimate for the fraction of the radius of the car is to the right of the vertical diameter? What would you estimate? Jacob, what do you think? What would you estimate it to be?
Well, I said cosine 3.
Estimate. You just estimate. Just guessing what it is.
The right vertical diameter.
Yeah. So, answer is, your estimate is?
4.25.
What's that?
4.25.
4.25? Okay, so that 4.25. Janessa, what do you think? What's your estimate for the fraction of the radius? 0.4. We got 4.25 and 0.4. 0.4. Yeah, fraction. It's a little bit less than a half, right? A little bit less than a half. So now I'm going to express this exactly in two different ways. Kelly, can you do one of the ways? What's one way we can express exactly the fraction of the radius that car is to the right of the vertical diameter? Oh no. Ouch. Jay. What's that? We want to express exactly the fraction of the radius that the car is to the right of the vertical diameter. We estimate it as 0.4. Now we want to calculate exactly. We can express it two different ways.
What would be a cosine of 3.5 over 8.5?
Cosine of 3.5 over 8.5. Nathan, what do you think about that? Agree with that?
No, it's gonna be 3.5 over 8.5.
Just 3.5 over 8.5. Maddie, what do you think?
I agree with that.
The last one?
Yeah, 3.5.
Right. If we want, yeah, we're just asking what fraction is 3.5 of the radius. So 3.5 over 8.5. That's one way to exactly express what that is. And is that like 0.4 something? What is it? 0.418? Okay. But anyway, this is an exact expression for that value. Okay, we need another way now. Allah, can you give me another way to express exactly how far to the right that car is in fraction of the radius?
Well, I'm only sure about the 3.5 over the 8.5.
Okay.
But I can think of another way.
We have do we have something else that will express that same value? Freddie? Radians. Radians is openness of an angle. Carla?
Cosine of the angle measure?
Okay. Which I'm showing as? Cosine of 3.5. Agree with that? Cecilia, what do you think?
Is it cosine of 3.5 over 8.5?
So 3.5 over 8.5 equals cosine of 3.5 over, someone else said that earlier.
Wait, are we finding the angle?
No, I'm asking to express the horizontal distance to the right of the vertical diameter as a fraction of the radius. What does that? Yeah, Jacqueline.
Cosine theta?
Cosine theta. What's the input into cosine? What does cosine take? Does it take 3.5 over 8.5? No, what does it take in? Angle of the swept counterclockwise from 3 o'clock, which is? In this scenario, what is that? Theta. All you know that is theta. Okay, so what I'm asking you to find is exactly cosine of whatever angle is swept counterclockwise from 3 o'clock. Both of those express the horizontal position of the car as fraction of the radius, cosine theta, and this ratio, 3.5 over 8.5. Okay, what about? No. No. This. No. Okay, how about express in two ways and estimate? So same thing now. The vertical distance above the horizontal diameter. So now it's easy. So you've seen an example, but still it's worthwhile to talk about. So same thing, estimate the vertical distance above the horizontal diameter as a fraction of the radius, and write two expressions that would find it. So estimate. What do you think for an estimate? Jenna? You estimate the vertical distance above the horizontal diameter as a fraction of the radius. She wants 0.9. Agree with that? Decent estimate? Negative? Positive? Positive. It's above, right? And it's almost all the way. So she's saying it's 9/10 of the way. Yeah, pretty good. Okay, give me one way to express that 0.9 exactly, right? That fraction of the radius length that it's above. So this is easy now. Dan, tell me.
Would it be like, well...
Oh, but I didn't tell you what this is. So I never told you what it was, right? So
So like,
there you go. Call it Y.
okay. As a fraction, so like, I mean the closest thing I can see is square root of 2.
Okay. We want an expression that gives exactly what the fraction of the radius is above the horizontal diameter.
Y over 8.5.
Sean, what are you going to say?
I was going to say sine.
Okay, so I heard Y over 8.5 and I heard sine theta. Sine theta, sine theta. That's exactly what the output of sine is. I'm asking you, what I asked you was exactly what sine outputs. And we could also write that as Y over 8.5. If Y is in feet. Okay, review. But we're going to come back to this a little bit later in class. Questions? Does it make sense? Basic definitions and This is the basics of trig right here. Any questions? Oh, I'm sorry. Go ahead. Estimate. So we're estimating what fraction of the radius the car is above the horizontal diameter. So we're estimating this dimension, or this red line right here, but not in feet as a fraction of the radius. So what fraction of the radius is that? Do you see that that's about 0.9? It's like you could compare it to a radius from here to here. And so it's like about 9/10. Better? Okay, cool. Other questions? Nice. Okay, so we got this is our typical situation. Our angle swept counterclockwise from 3 o'clock. And then we know we're graphing these relationships, right? By letting that angle be on the x-axis. And then we looked at different things, right? We looked at vertical distance above the horizontal diameter. And then we looked at horizontal position, horizontal distance to the right of the vertical diameter. So now I'm going to change. So tell me, the lengths of the black and gray lines, do they change when I change the... Yes or no? Do the lengths of those lines change when I change the radius of the circle? Yes or no? Some are saying yes, some are saying no. Discuss, or tell me your thoughts. Who said no? Why not?
Because the numbers aren't changing.
Because the numbers aren't changing? Like here the radius is 1,
Yeah, well, the radius is always.
and here the radius is 0.5. So do those lengths of the gray and black bars change or not when I change the radius? John?
Wait, we're talking about this side or this side? Because what I was going to say is because your radius always stays at one radius line.
Okay.
And it makes the same. It makes the graph on the right stay the same. No matter what.
No, we're not looking at the graph. Forget the graph on the right. It has nothing to do with the graph on the right. We're looking at the black and gray, the horizontal distance and vertical distance. When I change the radius of the circle on the left, do the lengths of those change or not? Dan, what do you think?
Yes. If we're using any kinds of units other than fractions and radian length,
Okay.
yeah, of course it changes.
All right. Well, what about if the unit is fraction of radius length?
It doesn't change. It's the same.
Okay, he nailed it, right? It depends. It depends on what unit you're using. If you're using feet or meters or miles or inches, then of course, when the radius gets bigger, those lengths get bigger. But I never told you what unit. So if you're using, and this is what Sean was getting at, if you're using units of radius length, then those gray and black bars are never changing in length as I change the radius of the circle. And that's exactly the idea of sine and cosine. All right, so now we want to introduce something new. A new length. Okay, and we're still going to measure it in radius lengths. We're still going to measure this in radius lengths. So we're going to take a vertical line, so kind of like sine, but instead of to the point on the circle, we're going to put this vertical line against the circle on the right-hand side. And we're going to use radius lengths to measure the vertical distance above the horizontal diameter to the terminal side, but not to the circle anymore, along this vertical line, which is up against the edge of the circle. Do you see that? Okay, so let's just kind of break this down. Let's look at the first quadrant. So this, in radius lengths, when theta is 0, what is the value of this quantity? Then we're in this new one, this blue one. So when theta is 0, what is it? 0. Okay? And then when theta is pi over 4. That's pretty close. When theta is pi over 4, what's the value of this quantity? Why 1?
Because it's just above the top.
just about at the top of the circle. Same level.
So it's like one radius length.
Oh, I see. I'm sorry, you're looking across. Yeah, okay. So at pi over 4, so by symmetry, won't this radius be the same as that right there? So it's like we make a square, right? It's like kind of like we're making a square. What angle would go through the corner of that square with side length 1? What angle would that be? That'd be our pi over 4, right? It'd be our 45-degree angle, or pi over 4. So when the angle is 0, this blue distance is 0 radius length. So when the angle is pi over 4, this blue length, this height above the horizontal diameter out against the circle out there, is 1. So let's see what happens now. So what happens now when I keep increasing the angle? What happens to that length? Getting close to pi over 2. It increases. A lot? Can I do it without going too far? Yeah, like a whole lot. Do you see that? So that, you can't really see it anymore, can you? So when this angle gets close to pi over 2, what happens to that distance that it will take to reach that terminal side? Yeah, that's an understatement, right? Okay, yeah, so really the closer we get to pi over 2, the more, it's like these are almost parallel, so it's going to just take like a whole long stretch to get up there, okay? So what's happening in the first quadrant? The length of this blue line starts at 0. Halfway through the quadrant, we're at 1, and then as we get close to pi over 2, it gets very, very large. And then what happens as soon as we change over pi over 2? Doesn't disappear, because now that terminal side intersects the line where? So now we have to extend that terminal side back down the other way, and now it intersects it down in the fourth quadrant. So now this is just like sine. If above is positive, then below is negative, right? So now all of a sudden it goes from a really huge positive number, and then it's crossed over pi over 2, huge negative number. Yes, sir?
What happens when sine equals 1?
When sine equals 1. Okay, good. So you're saying pi over 2.
Yeah.
What about at pi over 2?
It's like it would never actually...
Exactly. They're parallel, right? So I don't know if I can show that the way I've got it set up here. Yeah, that's the best I can do. So imagine that they're parallel. How long will that thing have to be before they touch? They'll never touch, right? So this length at pi over 2, then, this vertical distance above the horizontal diameter out at the right side of the circle doesn't have a value, right? It's undefined. It's like it gets closer and closer to just being forever. It will never intersect. And then as soon as we go over to across the boundary, it's a huge negative value, because it extends down below to intersect the terminal side, the pink side. Okay? So what would that graph look like? Yes. So now we're thinking about the graph over here. We said at 0, it's 0. Pi over 4 is about what, 0.75? Like a little more, 3/4 was 1. And then pi over 2 is about 1.5. So at pi over 2, or 1.57, we have a vertical asymptote, just like we had in our rational functions. It's going to get very, very, very large. But then as soon as it crosses over to pi over 2, the value of that thing is huge negative. And then when we get to pi, what about the value of that thing again? So here's negative getting less negative until we reach pi, and then this value is 0. Okay, so it's like sine, and it's the vertical distance above the horizontal diameter measured in radius lengths. But instead of the intersection of the circle, it's along this line. That's what to the circle? Tangent to the circle. Tangent. That's what this is. This is the tangent function. Okay, because that line, that blue line, is tangent to the circle. Okay, so does the length of that blue line change? Does tangent theta change when I change the radius? Does it change or not?
Does the what?
If I change the radius on you, like this, does the length of that blue line change? If you're measuring a radius length. No. If you're measuring a radius length, doesn't matter, just like the other ones. Doesn't matter what the radius is. That thing is the same. So this is what the graph of tangent looks like. Okay? So this is what tangent is about. It's very, very coherent with sine and cosine. It's the vertical distance above the horizontal diameter measured in radius lengths, but along the tangent to the circle on the right-hand side, along the vertical tangent to the right-hand side. Not tracking a point on the circle anymore, but intersecting outside the circle against that tangent line. Okay. So let's look at let's just look here in the first quadrant at some angle here. Something less than pi over 4. Okay? I want you to estimate sine, cosine, and tangent for this angle. Okay? So for this angle, estimate sine, cosine, and tangent. For the given situation here, estimate sine, and for the heck of it, estimate theta, right? Estimate theta. Based on an understanding of radians, not something you memorized, okay? So estimate theta based on what measuring in radians means, not something you memorized, i.e. key angles. So let's do theta first. What would you estimate theta to be? What do you think? Andrew? How many radians? 35 radians.
Uh,
0.8 radians. What do you think? What's that?
So I think it's smaller.
Smaller than that?
0.3.
What's the calculator for?
What? I'm not even.
You're not using it. Okay, what were you going to say?
I'm gonna guess it's just a little under pi over 4.
Okay, so, but again, it's not based on something you memorize. We want to, based on what radians are about. Yeah, Janessa.
Like 0.3 or 5,
0.3 or 0.4? All right, so we got 0.8 and 0.3 or 0.4. Where is 1 radian? So if we took that radius and wrapped it on here, it's about like that. So we got 0.8 and we got 0.3 or 0.4 or something new. Nathan, what do you think?
Well, we're looking for theta, right?
Theta. We're just estimating theta based on our understanding of radians.
So,
So 0.3 or 0.4, 0.8 or something else.
Yeah, I'm gonna go with 0.8.
0.8. What do you think, Faisal?
I think I go with about 0.6.
So yeah, it looks to me like 0.7, 0.8, right in there, right around 0.7. So 0.8 is not bad. It's about 7/10. That radius, that's about 0.7 or 3/4 maybe, 3/4 of a radian, 3/4 of a radian. All right, what about sine theta, cosine theta, tangent theta? So do these. Kate, what about sine theta? What do you think for sine theta?
Like 0.65.
0.65. Okay, something a little bit more than halfway. Good. Cosine theta. Fahia, what do you think for cosine theta?
0.8.
About 0.8, right? You can see it right there. About 0.8 for cosine theta. All right, what about tangent theta? What do you think? Yeah?
I think 0.75.
0.75. Maybe 0.7. Yeah, maybe 0.7. All right? Okay, so if we labeled this x, y, and what should we label this? R for the radius? Okay, can you express them exactly now? So let me change it. So that's good. So now express cosine, sine, and tangent exactly. This is going to get really cool in a second. Don't fall asleep. I want to express cosine exactly. Sean, how would I do that? Sean.
X over R.
He wants x over r. Agree? You got it, right? So it's whatever this distance x is as a fraction of the radius. Sine theta. Y over r. That's easy now, right? What about tangent theta? Takes a little more ingenuity. Tangent theta. Sean wants to answer. And why would it be y over x if it's this length right here?
Because it's
Right, so we're saying it's the length of the blue measured in the radius, in the unit of the radius. So why would it be y over x? You can see why it would be? Okay, but if we're using our definition that it's this length in radius lengths, how is it y over x? Yeah, that's true. But I want to say, okay, tangent theta is this length in radius lengths. How is it the same as y over x? Because what? This is how I can see it. What do we have? You see what we have in geometry there? Looking at y over x, but then looking at this triangle here. Similar triangles, right? This tangent theta divided by, this will always be 1, right? No matter what the size of the circle is. So tangent theta over 1 by similar triangles will equal y over x, right? Do you see it? Okay, so then we've got this right triangle here, and we've got some names based on the right triangle and based on what that angle is. So because the hypotenuse is the long side, opposite the right angle. Where am I? There we go. Hypotenuse is the long side across from the right angle. And then there's two legs, right? Two legs. One leg is next to the angle theta. We call that adjacent. One leg is across from theta, so we call it opposite. It's opposite the triangle from theta. So now, express cosine theta, we said it was what? X over r. Well, that's the same as saying adjacent over hypotenuse. So this adjacent over, you guys have learned these before, adjacent over hypotenuse. The meaning of that is still the fraction of the radius length to the right of the horizontal vertical diameter, because the adjacent is that actual measure, the hypotenuse is the radius. So that ratio is still the fraction of the radius to the right of the vertical diameter. So what about sine theta? Yeah, you said y over r, because you were saying, oh, it's the height y, but relative to the radius, or in the units of the radius. So we can just rewrite that as opposite over hypotenuse. So these triangle ratios with opposite, adjacent, hypotenuse, they're really nothing new. They're just new names for vertical height, horizontal distance, and radius. Okay, so tangent is? Opposite over hypotenuse, or opposite over adjacent. Okay? So what happens is then now we can take this right triangle and kind of apply it in the real world and imagine the circle, but then we've got these ratios with the sides of the triangle that we can apply to the meanings of sine, cosine, and tangent. Okay, so does it make sense? The feeling of excitement in the room wasn't as exactly what I hoped.
We're thinking of the test.
But still, this is all the principles of the test, right? We're just renaming horizontal distance. We're renaming vertical distance. And we're renaming the radius using these names of the triangle, using these names of the legs in the triangle. Okay? So it's still the meaning behind it is still, we still have it. Okay. So go to, in your workbook, hopefully you still brought that. Module 8, Investigation 1. Module 8, Investigation 1. So I want you to do 1, 2, and 3. But here's the key thing. We've had to relate it back. So now we're just given this right triangle. So we want to relate this back to our circles. So we're going to draw the circle. Okay, so here's the thing that's when they draw the circle, students kind of mess up. So both AB and BC they're not both the radius. That's what students do. They go like this. They go. When they're drawing these circles, they go, okay, here it comes. It's coming around like this, and then it comes around like this, like that. Okay? So don't do that. One of those is the radius. They're not both the radius. Okay? So decide which one is the radius, and then draw your circle accordingly. Okay? And then you're going to be setting up exact expressions for sine, cosine, or whatever they ask for, without finding the angle. This is the whole point. If we have those lengths, like we've been doing earlier in class, we have those lengths. We can express sine, cosine, and tangent through their meanings. Okay. So you're going to draw the circle correctly, the best you can to draw the circle, and then whatever they ask for, you're going to whether it's sine, or cosine, or tangent, or maybe more than one. Express those using the legs of the triangle, not by finding theta. Okay? Go. So make the best. Okay, so you can check what you got for number 1. Your sketch for number 1. Sine theta equals? It's still the vertical distance above the horizontal diameter as a fraction of the radius length. So we're going to take that 3 as a fraction of the radius length. It just happens that in that triangle, 3 is the opposite side, 5 is the hypotenuse. It's still the vertical distance above the horizontal diameter measured as a fraction of the radius. Questions? Good circles. You got something to draw circles with? Oh, okay. That's fine. I should put it on mine. And then, so if you want to do cosine, look at 2a. If you want to do cosine, is it going to be 2.4 over 4? How are you going to get that? So we need that length BC, horizontal distance, right? Or the adjacent side. How are we going to get it? Exactly, right? So we'll just call it x, sure. So then you can use the Pythagorean theorem to solve for the side that you need. Cosine theta equals? What does this become? Is it, are there more decimal places? No? Just 3.2? So cosine theta is 3.2 over 4. It's still the horizontal distance to the right of the vertical diameter to that point, right? Still that 3.2 measured in the units of the radius, 3.2 over 4. It's just that 3.2 is adjacent to the angle theta, and 4 is the hypotenuse of the triangle. So adjacent over hypotenuse. Okay, how about this one where the triangle's the other way? How do we reason about that? So this one. So triangles, right, can be stretched, shifted, rotated, and so we need to kind of like loosen our grip on angle swept counterclockwise from 3 o'clock. All right, so how can we still make sense of this in our circle, right, with our angle swept counterclockwise from 3 o'clock? So it's easy to just set up the adjacent, right? Just identify what side you have. So what side is this? Adjacent, opposite of hypotenuse. Okay, that's the hypotenuse. This one is opposite if we're talking about this angle. If we were talking about this angle up here, then this becomes the adjacent side, okay? So it depends on the angle, right? It's got to be the one that's opposite the angle. This is the adjacent. So how can we relate this to the we can set up the ratios and we can get sine, cosine, and tangent right just by setting up the ratios. But then how can we relate it to the fact that we said it was always rotated counterclockwise from the 3 o'clock position? How can we relate it back to that? Because I know you want to do that really badly, right? How can we? We make this the center of the circle. How can we relate all these ratios back to theta being an angle swept counterclockwise from 3 o'clock? What's that? Flip the triangle. That way. What were you going to say?
Oh, I was gonna say you could make the 8.3 negative.
Okay. All right, but if you do that, but then we're really talking about a different angle then, right? We want to preserve this angle. So I think their idea of flipping the triangle is a good one. And then imagining the circle. Help me. Here we go. Every once in a while. Okay, so now where's theta? It's there, and this is 8.3, and this is 10.6 here, and this is 10.6 here, and this is 6.6 here. This is our radius out to here, right? So we got our full radius. So you flip it now, everything is okay, and everything is symmetric, and we get all the same values for sine, cosine, and tangent. Because sine now is going to be, now we have our nice 3 o'clock angle, measured counterclockwise from 3 o'clock, and we would have all the same ratios when it came to opposite, hypotenuse, and adjacent. So this allows us to kind of extract a right triangle from the circle and then flip it, rotate it, and still these ratios still are maintained. So we can apply it to all kinds of real world situations. Okay, questions on these problems? Okay, try number 5. So flip over to number 5. This says 6 centimeters, this says 2 centimeters. Now we're going to look at 2 different angles. So beta and alpha. And when you change the angles, so what is the opposite side for alpha? What's the opposite side for alpha? The one that has length what? 6. Okay, opposite means across from the angle, right? Opposite. I'm opposite the room from Janessa, right? But I'm adjacent to the front row. Okay, so I'm next to the front row. So what's the opposite side for beta? The one that has length 2. Okay, so when you change the angle, right, you have to change your opposite and your adjacent. Flip. Okay, no calculator. We want exact results, we want exact expressions for all these without finding the angle. Without finding the angle, so we want exact expressions. No calculator. No calculator. Who is doing this opposite adjacent hypotenuse for the first time? You've never seen this before in a math class. It's okay. So Aaron, is it making sense? Okay. Because I know many of you are holding on to some things you learned in the past, so I don't want to go too fast. What'd you get for the hypotenuse? No, exact. We want exact results. Square root of 40. And if you want, that's 2 radical 10. Take your pick. So everything exact. Exact. And once you get those 6, you're confident about those 6, then I want you to, now part G, determine the measures of the angles. How can we determine the measure of the angle? Good practice for the exam.
Wait, is this going to be on the exam?
No, but we're using ideas that are going to be in the exam. No, of course not. Of course not. New things that we're learning today are not in the exam, but we're using lots and lots of things we learned before. Yes, the what we're going to do today. Definitely. That was all the stuff we did today. Okay, tell me how you determine angle alpha. Anyone got alpha yet? I'll figure out what the angle alpha is. So that's going to definitely be with your calculator. Yeah. So, but we should be able to express it exactly. That's good. So we should be able to express it exactly, but then get an approximation with the calculator. So let's see. Still working hard. Cecilia, did you get angle alpha?
No.
Could you?
I think I
Could you get it? How would we get angle alpha from all this stuff?
It would be 6 sine theta is equal to something, and then you would do the sine inverse of that to find the angle. But I don't,
6 sine theta equals something?
yeah, I don't know what the.
But didn't you find sine of alpha? Didn't you already?
Oh yeah, I put 6 square root of 40 over 40. I didn't simplify it.
So sine alpha equals what?
6 square root of 40 over 40.
6 square root of 40 over 40?
Did you have radical denominator, right?
Oh, I see. Over regular 40, like that.
Yeah,
Okay,
I just multiplied it by.
got it. Okay. Yeah, so right. So we could start with,
Or do you just want 6 over square root of 40?
just to see where it came from.
Okay.
So she then simplified that to 6 radical 40 over 40, which could be further simplified to,
12 square root of 10 over 40.
yep. And finally, 3 squared of 10 over 10. There would be lots of ways to get there. That was one way, okay? But so it's sine alpha, 3 squared of 10 over 10. To find alpha then, okay? So if this is a vertical distance above horizontal diameter, we can put that into arc sine, sine inverse. And we can get an approximation. It gives us approximation of. Let's do degree. Anyone got degrees? Right? Yeah. 0.57. Okay, that's just an approximation. What's 61 or 161? That's not right, right? It's not going to be 150 degrees. Something's wrong. Sean, what'd you get?
71.
That sounds better. 71 point. That's an approximation, right? Okay, questions on that? So now, and then finding beta, you could, there's different ways you could express alpha. You could do the arc cosine of, what, 2 over radical 40. Arc cosine of 2 over radical 40 would find the same angle measure. Or using beta, okay? So to find beta, you could go back to your arc sine or cosine, or what could you do to get beta now? Sum of the angles in a triangle is 180 degrees, okay? So we could take, and so for a right triangle, the sum of the two short angles, or smaller angles, is what? No, the sum of the two. So the sum of your two smaller angles in a right triangle would be 90, because your 90 is taken up by that right angle, so the remaining angle measure has to total up to 90. So that's another way we could find beta. Let's just take 90, 71.56 away from 90, but then that's just an approximation. Okay. So let's try this example and make up one here. Important example that's not around here. Let's do this. Oh, that's not right. What am I trying to do here? Okay, so it doesn't, you can't get that with right triangles. Okay, I'm just kidding. All right, so let's talk about some applications here. Oh, by the way, here's final exam. A week from Tuesday.
7 p.m.?
7 p.m. Yes, 7 p.m. Okay, and it's in PSF 166. So PSF is what? It's between the Palm Walk and Goldwater, or the engineering library, science library. So PSF is kind of halfway between Goldwater building and Palm Walk. Where's what?
The philosophy room?
Philosophy room. I don't know about philosophy room. That's not a philosophy building. It's physical science. Physical science, wing F. Okay, here we go. So we can use this stuff to find very useful things, like the height of a tree that's really tall that we don't want to use a tape measure for, right? So it's dangerous. So we can use, by using angles and triangles and our relationships that we just learned, we can find the height of the tree. So this is any surveyors, what is this called? That shoots angles, what's that called? Anyone know? Angle shooter, right? So it's the thing, it shoots angles. It measures angles. So this is called an angle of elevation. An angle of elevation is an angle swept up from horizontal in any direction, okay? So this angle of elevation is 39 degrees. The distance of the device is 70 feet from the tree. And the device sits 3.5 feet above the ground. We want the height of the tree. So we want to find the height of the tree. Yeah, Dan.
How old is this mathematics? When was it discovered?
Like right triangle trigonometry, that's a great question. I don't know what era that came about. Google does know. All right, so we want to apply triangle. So can you envision the triangle you're going to use to do this problem? Can you envision the triangle you're going to use to solve this problem and find the height of the tree? Are you going to use the ground as the base of the triangle? Yes or no? No. This is what you should be envisioning. What I've done in red here. That triangle is going to be useful, okay, because so now our base is 70, right? If you use the ground, then the base isn't 70 anymore. We don't know what the base is. Okay, go. See if you can find the height of the tree. So you're applying these triangle relationships that we just learned or that you've known from the past. Find the height of the tree. Okay, so the idea is we have these relationships like sine theta equals opposite over hypotenuse, say. If we had any two of those values, we could find, so if we had theta and the hypotenuse, we could find the opposite side. If we had the hypotenuse and the opposite side, we could find sine of theta, and we could find theta. So having any two values, you're going to look for the relationship that brings together the values that you know and the one that you're looking for. Okay, so what relationship applies here? So Jonathan, did you make any progress on this one? So if we had this angle 39 degrees, Jonathan, what side would this be relative to the 39 degrees? Adjacent, okay? And what side are we looking for? Opposite, right. So, look, we've got the angle, we have the angle and the adjacent, and we want the opposite. Which of our relationships brings those three things together? Right. So, tangent of the angle, which is, now we know the angle, right? So this is a little different. We know the angle. So tangent of 39 degrees equals the opposite over 70, adjacent. So you find the things that you know and what you don't know, and you're going to pick the relationship that brings those together. Okay? Find the quantities that you know, the ones and the one that you don't, and for the easy problems anyway, and then you're going to find the relationship that brings those together. So the opposite side is 70 tangent 39 degrees. Make sure your calculator is set to degrees. What do you get? I heard 56.68. What's the units on that? It's the opposite side. It's kind of the same units as the adjacent side, so feet. So that's the height of the tree, right? Oh, you're so smart. The height of the tree is? We got the opposite side, but we got 3.5 more feet to add. 60.18 feet tall. Pretty slick. Didn't even have to climb the tree. Okay? Didn't even have to climb the tree. We just calculated the height of the tree. Questions on that example? Okay, so here's some terms that you'll hear. Okay? We just talked about angle of elevation. It's an angle swept up from horizontal. That's easy, right? So you got horizontal, swept elevation, make angle of elevation. Angle of depression is more tricky because you can set up a triangle here, and you can easily blow this, all right? Angle of depression. So we got two triangles here. So often students, incorrectly, they set this triangle up and then they put their angle of depression here. Okay, be careful. It's the angle swept down from horizontal. It's the angle swept down from horizontal. It's not this angle that I have an X, right? That angle that I have an X is not an angle, that's kind of like an angle swept up from vertical. So you want what measure of depression? So you have to start at horizontal. how far tilted downward, or what openness down from horizontal. Okay, so watch out. This is an easy mistake you can make, labeling what I've done in red as angle of depression when it's not. That's the complement. That's 90 degrees minus the angle of depression. Okay? Be careful. Go. Your turn. When a ship has an anchor 200 meters to the ocean, certain location, the rope's angle of depression is 53 degrees, assuming the ocean floor is level. What is the depth of the water? Go. Figure it out. Yeah, check with each other. See if you get it.
Minus. Negative.
Questions? Yeah. You got the right triangle. The correct triangle. So that's your angle of focus. No. You gotta isolate this one first. It's always the hypotenuse, regardless of which angle you choose, because it's the side opposite the angle you choose. The only thing that flips is the adjacent and the opposite side. So that's your adjacent leg, right? So adjacent is referring to the leg, hypotenuse is the long side. So they'll always. They'll do it. Questions? Did you do that?
Yeah, so it's like when it's the first time, it's the first time it's.
Did you grab it to make your notes right now? Yeah, cool.
It's a lot easier than trying to draw.
Well, yeah. Okay, let's see. Who's gonna help me? Aaron, did you make some progress on this? Tell me. What'd you do first?
I figured out
So, but you had to do something first. What did you do first?
I drew it out.
Okay, so what did you draw?
I drew it. Exact triangle that I was doing.
Okay, so did you make a triangle like this, triangle A, or did you make a triangle like this, triangle B?
Triangle.
Like this, triangle A, or like this, triangle B?
No, the second one.
The what?
The B.
The second one. You made this triangle.
Yeah.
Okay? Is that what you did? That's okay if you did. That's fine.
Yeah, but I just did it the other way. I don't know, it's the same thing.
You did it the other way. You did this triangle down here. No?
Yeah.
All right, you did this triangle. Right?
Here, now it's black.
Okay. So, is this 53 right here? So it says the angle of depression is 53. Is this 53?
No, the other one.
It's this one. Okay? So did you use this triangle or did you use this one?
I used the first one, but upside down. Alright, I drew it.
Oh, you flipped it up.
Yeah,
So you took it and you flipped it up like the anchor was up here.
yeah.
And you made the anchor up here.
There you go. That was fine.
Okay? Great. And where's our 200?
It's on the button.
Hypotenuse. And you want to find which? Adjacent or opposite?
Opposite.
Opposite? Which did you use then? Which of the... Fine. So sine of 53 degrees equals?
Y over here.
What'd you say?
Okay, yeah, never mind. That works.
Yeah, opposite over hypotenuse, right? Opposite over hypotenuse, or vertical height as a fraction of the radius, right?
Yeah, that's
Vertical.
the Y.
Yeah. Okay, what do we get?
I got 159.7.
Someone else? 159 point. And then what's the units? Meters. Okay, so then, really cool. Same as the tree problem, but what if you don't know your distance to the base of a mountain, right? Because it's under the mountain. You can measure your distance to a tree and get that horizontal, but you can't measure the distance to the base of the mountain. So this is what you have to do. You have to take two angle readings at different distances from the mountain. So they took the first angle reading here at 35 degrees to the top. And then they took a second angle reading, 30 degrees, 1,500 feet further away from the mountain. And so the question is, how tall is the Matterhorn? So that's harder. It's not hard, it's a little harder, but it's not hard. You can do it. You just have to have the right, you have to combine some relationships here and do some algebra and use our relationships more than once. Okay? Because you got more than one triangle at play here.